To solve equilibrium problems that have initial amounts, we're going to first make sure we have a balanced equation. Then we're going to set up an ICE chart, which is your initial concentrations. Then we define the change needed to reach equilibrium. Then we define the equilibrium concentrations by applying the change to the initial concentrations. Then we write the equilibrium expression, plug in all of our equilibrium concentrations into that expression, and solve for the unknown. If our K is less than 1 times 10 to the negative 4th, we can ignore the minus x. Because when K is less than 1 times 10 to the negative 4th, that means we have very few products. And subtracting x is probably going to be a negligible amount. So after you solve for x, if you ignored x due to the small ka, you have to calculate the percent dissociation. If it was less than 5%, then you were correct in your assumption to ignore x. If not, you have to go back and solve for x using the quadratic equation. So percent dissociation is whatever you calculate x to be over the initial concentration you had times 100. So let's go through those steps in this problem. We know this problem is going to be different than what we solved previously because it says that we just placed a mole of NaOCl in a 2-liter flask. And it's asking what do we have at equilibrium. Remember that in the equilibrium expression, you can only plug equilibrium values. So we're going to have to set up our Rice chart. And that stands for reaction. So we have our balance to reaction. I should be our initial concentration. It's a 2-liter flask, so 1 divided by 2 is 0.5 molarity. They didn't say anything about NO or chlorine, so those are initially 0. For our change, since these are NaOCl is a reactant, it should be going down by 2 times some amount. We put the 2 because of that coefficient. X because we don't know how much it's going down. On the product side, our product should be going up, so those are going to be plus. Again, we have a 2 in front of NO, so that should be plus 2x. And chlorine's going up by some amount, but only a 1. Since I don't know what x is, I'm going to look at my equilibrium line and say that it's going to be 0.5 minus 2x. NO will just be 2x because 0 plus 2x is 2x. And chlorine will just be x. Writing my equilibrium expression, and plugging in my values to it. I look now and see that that will lead to the quadratic equation, but my k is less than 1 times 10 to the negative 4th. So I'm going to ignore that minus 2x. It doesn't matter if it's a minus 1x or 2x or 3x. If it's a minus x, we can ignore it. We cannot ignore the x's on top, though. So simplifying that, and in this problem, we know what x is, or k is. We have 1.6 times 10 to the negative 5th times 0.5. Here, since we have a square and a 2, then that's going to be 4 squared times x is 4x cubed. Divide by 4 and take the cube root. On your calculator, that's under the math button. So X is 0.0126. Since we ignored the minus X, we have to go back and make sure that we could actually ignore that minus X by saying 0.0126, which is X, over my initial concentration times 100. That's a 2.52% dissociation, which means we were correct in our assumption of ignoring minus X. Finally, the question asked, what are the equilibrium concentrations? So 0.5 minus 2X is 0.47 molarity. 2X is 0.0252 molarity. And X is just 0.0123 molarity. This one should actually just be 0.025 molarity for 2 sig figs. And finally, it asked, are the reactants or products favored? Since my K is very small, the reactants were favored. So let's look at another one. On this one, my equilibrium constant is 5.1, which means the products are favored. I know I'm going to need a Rice chart because, again, it says that I initially have 1 mole in a 1 liter flask. So I'm calculating equilibrium, which means I don't have equilibrium. So it says that I have 1 mole of each component. 1 divided by 1 is a 1 molarity. So I have 1 of everything. Then for my change, remember my reactant should be going down. My product should be going up. They all have coefficients of 1, so that's going to be a minus X, plus X, and plus X. And for my equilibrium, it's just 1 minus X. So remember, this is basically our equation line. So 1 plus X and 1 plus X. So to solve this one, we write our K expression. And then we plug everything in. Again, our K from this problem was 5.1. Since both of these are the same value, I can just write 1 plus X squared. And both of these are the same value, so I can say 1 minus X squared. I cannot ignore the minus X in this case because my X, or my K, is much larger than 1 times 10 to the negative 4th. But I have squared on top and bottom. So if I square root both sides, the square root of 5.1 is 2.26. Then I get 1 plus X and 1 minus X. So to solve this out, you do need to distribute it out. Combine like terms. And so X is equal to 0.387. So my concentration of CO2 is equal to my concentration of hydrogen, and that's 1 plus 1.387, so 1 point, and we want 4 sig figs. And my CO is equal to my H2O, and that's 1 minus X, and that's the end of the problem. Go ahead and try this next one on your own. Restart when you have an answer. All right, so the first thing you should have done is drew your rice table. And for our rice table, it says that we have 3 moles of each component in a 1.5 liter flask, which means 3 divided by 1.5 is 2 molarity, 2 molarity, and 2 molarity. Your reactants should have went down by some amount. They both have coefficients of 1, so these both should have been 1x. And then my product should have went up by 2 times that amount because it's 2x. So at equilibrium, I have 2 minus x, 2 minus x, and 2 plus 2x. Looking at my K, my equilibrium constant is much larger than 1 times 10 to the negative 4th, which means the products are favored, and I cannot ignore my minus x's. So setting up my KEQ expression, plugging everything in, again, since both of my reactants are 2 minus x, I can combine that to be 2 minus x squared. So just like the last problem, I can square root both sides. Multiply both sides by 2 minus x. So combining like terms, when I add 10 plus 72x plus 2x, I get 12.72x. And when I subtract 2, then I get 19.44. That's how we got that. Dividing by 12.72. You get x is 1.53 molarity. So bringing that back, that means my concentration of H2 is equal to my concentration of F2. And that's 2 minus 1.53, or 0.47 molarity. And HF is equal to 2 plus 2x, or 5.06 molarity. Again, I'm getting these values by plugging x back into this equilibrium line. So on this one, our KEQ was really small, so the reactants are favored. They gave us molarity, and so we're going to need to set up a race chart. We have 0.53 molarity. We do not have any of these two because it didn't say we did. And then our change line should be minus x, plus x, and plus x. So at equilibrium, we have 0.53 minus x, and x. Writing our KEQ expression, plugging in all our values, ignore minus x since our KEQ is less than 10 to the negative fourth. Multiply by 0.53. X squared is equal to square rooting x is equal to 0.00272. Because we ignored the minus x, remember that we do need to calculate our percent dissociation. So that's our x over initial concentration times 100. We get 0.51%. That's much less than 5%, so we were good in our assumption. And so our equilibrium concentrations we got 0.53 minus x gives me a final concentration of 0.5727, and our concentration of H is equal to concentration of C6H4NO2, and that's X.